On April 8, 1941, at exactly 2:35 in the afternoon, a massive aircraft rolled down the runway at Nakajima's test facility outside Tokyo. The plane was enormous, over 100 feet long, with a wingspan stretching nearly 140 feet, for engines roared as it lifted into the humid Japanese air. Engineers from the Imperial Japanese Navy stood watching, their faces tight with anticipation. They had spent 18 months building this bomber. They had spent $950,000 buying the American airliner it was based on. They had faked a crash to hide what they were really doing. And now, finally, their creation was airborne. The pilot pushed the throttles forward. The aircraft climbed slowly, too slowly. The engines strained against the weight. The controls felt sluggish, unresponsive. Something was wrong. Something had always been wrong. The Japanese had stolen American technology, reverse-engineered the most advanced airliner in the world, and transformed it into what they hoped would be a strategic bomber capable of striking targets across the Pacific. Instead, they had built one of the worst heavy bombers in aviation history. This is the story of how Japan bought America's rejected airliner and turned it into a spectacular failure. It is a story of espionage, deception, engineering hubris, and the dangerous assumption that copying someone else's work is the same as understanding it. It is a story that begins not with war, but with the golden age of American commercial aviation. The year was 1935. Commercial aviation was transforming America. Airlines were expanding routes. Passengers were growing more confident in air travel. And aircraft manufacturers were competing fiercely to build the next generation of airliners. The Douglas Aircraft Company had just introduced the DC-3, which would become the most successful commercial aircraft of its era. But even before the DC-3 entered service, the airlines were already dreaming bigger. William Patterson, the president of United Airlines, approached Douglas with an ambitious vision. He wanted an aircraft that would make the DC-3 look like a relic. Patterson envisioned a four-engine airliner capable of crossing the entire continent without stopping for fuel. It would carry 40 passengers in daylight service or 30 in sleeper berths for overnight transcontinental flights. It would have pressurized cabins so passengers could fly above the weather. It would have air conditioning for comfort. It would represent the absolute cutting edge of aviation technology. The proposal was audacious. No airline had ever operated a foreign land plane for commercial passenger service. The technology Patterson was describing barely existed. Building such an aircraft would require solving engineering problems that had never been tackled before. The risks were enormous. The costs would be staggering, but the potential rewards were equally impressive. Whoever built the first successful four-engine airliner would dominate commercial aviation for a generation. Douglas was intrigued but cautious. They knew the challenge would stretch their capabilities to the limit. They agreed to proceed only when other airlines expressed interest. American Airlines wanted in. Eastern Airlines joined the consortium. Pan American Airways and Transcontinental and Western Air, which would later become Transworld Airlines, also committed to the project. Each airline contributed $100,000 toward development costs, creating a $500,000 fund to support the most ambitious commercial aircraft ever attempted. The engineering challenge was immense. Douglas assembled a team led by some of their best designers. Arthur Raymond, who had led the DC-3 program, took charge of the effort. The team faced problems that had never been solved before. How do you build a wing strong enough to support for large engines while remaining light enough to fly efficiently? How do you design landing gear that can handle an aircraft weighing over 60,000 pounds? How do you route fuel lines, hydraulic systems, and electrical wiring through a fuselage that must also accommodate passengers in comfort? The questions multiplied as work progressed. How do you pressurize a cabin at high altitude without creating structural stress that would lead to metal fatigue? How do you provide enough auxiliary power to run air conditioning, cabin lighting, and galley equipment without overloading the electrical system? How do you train pilots to fly an aircraft twice as heavy and twice as complex as anything they have operated before? The team worked for 2 years. They produced 8,100 drawings documenting every aspect of the aircraft. They built a detailed wind tunnel model and conducted 866 separate tests totaling 1,100 hours. They studied airflow patterns, stability characteristics, and control effectiveness at speeds and altitudes that no previous airliner had achieved. They used 1,300,000 rivets to assemble the prototype. The total engineering effort was measured at 500,000 man-hours, an unprecedented investment for a commercial aircraft. What emerged was unlike anything the world had seen. Douglas called it simply the DC-4. The aircraft was a marvel of innovation from nose to tail. It was the first large aircraft with tricycle landing gear, meaning it sat level on the ground rather than tilting back on a tail wheel. This seemingly simple change had profound implications. Passengers no longer had to climb uphill to board or walk downhill to exit. Cargo loading was easier. Ground handling was more predictable. The aircraft looked modern because it was modern. The nose wheel design would eventually become standard across the industry, but in 1938 it was revolutionary. The wing was massive, spanning over 138 feet from tip to tip. It had to be that large to generate enough lift to carry the aircraft's weight while maintaining acceptable landing and takeoff speeds. The wing design borrowed from the proven DC-3, but was scaled up dramatically. For Pratt & Whitney, our 2,180 Twin Hornet engines were mounted on the wings, each producing 1,450 horsepower. The engines were positioned with noticeable toe, meaning they were angled slightly outward rather than pointing straight ahead. This unusual arrangement was designed to improve stability by creating favorable yaw moments during single-engine operation. The tail was perhaps the most distinctive feature. Instead of a single vertical stabilizer like most aircraft, the DC-4 had 3 vertical fins, one in the center and one at each end of the horizontal stabilizer. This unusual configuration was chosen for a practical reason that illustrated the constraints commercial aviation operated under. The aircraft was so large that a single conventional tail would have made it too tall to fit inside existing hangars at airports across the country. Airlines could not afford to build new hangars at every destination. The triple tail kept the overall height manageable while providing adequate directional control. It was an engineering compromise dictated by economic reality. Inside the fuselage, the DC-4 was designed for a level of luxury that commercial passengers had never experienced. The cabin was wider than any previous airliner, allowing for more comfortable seating arrangements. Passengers sat in chairs that actually resembled furniture rather than the utilitarian benches of earlier aircraft. The aircraft could carry 40 passengers in a standard configuration, but Douglas also developed sleeper variants with fold-out bears for overnight flights. Passengers could board in New York, eat dinner, sleep in an actual bed, and wake up in Los Angeles. Air conditioning kept the cabin comfortable regardless of outside temperatures. The design even included provisions for cabin pressurization, though this system was not installed in the prototype. The flight deck was equally advanced. Power-boosted flight controls reduced the physical effort required to fly the large aircraft. Without power assist, the control forces would have been so heavy that pilots could not have maintained precision during landing or maneuvering. An alternating current electrical system provided reliable power for instruments and systems. This was unusual for the era when most aircraft used direct current exclusively. Auxiliary power units could provide electrical and pneumatic power on the ground, eliminating the need for external ground equipment at remote airports. On June 7, 1938, the DC-4 prototype was ready for its first flight. The location was Clover Field in Santa Monica, California, where Douglas had its main factory. At the controls was Carl Anson Cover, Douglas's chief test pilot and one of the most respected aviators in America. Cover had a remarkable career that mirrored the development of modern commercial aviation. Born in 1893 in Pennsylvania, he had learned to fly in the Army during World War I. He became a test pilot after the war and eventually joined Douglas in 1930. He had flown the first flights of the DC-1 in 1933, the DC-2 in 1934, and the DC-3 in 1935. He had literally piloted the development of the aircraft that made commercial aviation practical. Now he was adding another milestone to his already legendary resume. Cover ran through his pre-flight checks methodically. His decades of experience had taught him that thorough preparation prevented deadly surprises. The 4 engines were started one by one, each twin Hornet coming to life with a distinctive rumble. The aircraft registered as NX-1810 with construction number 1601 rolled toward the runway. The ground crew watched with a mixture of pride and anxiety. 2 years of their work was about to be tested. Cover advanced the throttles and the big aircraft began to accelerate. The DC-4 was heavy and used a lot of runway before reaching flying speed. At the proper airspeed, Cover pulled back on the control column and the aircraft lifted into the California sky. The most advanced airliner ever built had taken its first successful flight. The flight lasted about 45 minutes and went without incident. Cover landed and reported that the aircraft handled reasonably well, though there were characteristics that would require further investigation. Testing continued through the summer and fall of 1938. Douglas pilots evaluated the aircraft's handling characteristics at various speeds and altitudes. They tested its performance in climbs, descents, and turns. They examined the reliability of its complex systems under the stress of repeated operations. Problems emerged as they always do with new aircraft. Some systems did not work as designed. Some performance numbers fell short of predictions. The type certificate was delayed while issues were addressed. On May 5, 1939, the Civil Aeronautics Authority finally granted approval. The DC-4 was officially certified for commercial operation. The prototype was turned over to United Airlines for in-service evaluation. This was the moment of truth that would determine whether the DC-4 was a breakthrough or a disappointment. Test flights with professional test pilots were one thing. Daily airline operations with revenue passengers, tight schedules, and maintenance constraints were something else entirely. On June 9, 1939, something remarkable happened that connected the DC-4 to aviation's earliest history. The aircraft was in Dayton, Ohio, a city with deep significance to American aviation. Dayton was the hometown of Wilbur and Orville Wright, the brothers who had invented powered flight. Carl Cover brought the DC-4 to Dayton for demonstrations, and a very special passenger came aboard for a flight over the city. That passenger was Orville Wright himself, then 67 years old. Orville had been just 32 when he and his brother made the first powered flights at Kitty Hawk in 1903. That first flight had lasted 12 seconds and covered 120 feet. Now 36 years later, Orville sat in the cabin of a four-engine airliner that could carry 40 passengers across the continent. He looked down at the city where he had grown up, where he and Wilbur had built their first flying machines, where the bicycle shop that funded their experiments still stood. The flight was a bridge across generations of aviation progress. The man who had invented the airplane was now flying in its most advanced incarnation. Cover later said it was one of the proudest moments of his career. The photograph of Wright in the DC-4 cabin became an iconic image of aviation history. But despite successful test flights and the presence of aviation's founding father, United's evaluation revealed serious problems that threatened the entire program. The DC-4 was too complex for practical airline operation. Its sophisticated systems required specialized maintenance that most airports could not provide. Mechanics trained on DC-3 South were baffled by the DC-4's electrical systems, hydraulic circuits, and control mechanisms. Operating costs were far higher than projected because of the time and expertise required to keep the aircraft flying. The aircraft consumed fuel at alarming rates. The four engines drank gasoline faster than anyone had predicted. Range was less than promised because fuel consumption exceeded design estimates. Performance fell short of specifications in almost every category, especially after the seating capacity was increased from 40% to 50% to passengers to improve economics. That change pushed the gross weight up to 65,000 pounds, far above the original design weight. The fundamental problem was weight. The DC-4 had grown heavier throughout development as engineers added systems and strengthened structures to solve problems that emerged during design and testing. Every solution to every problem seemed to add more weight. The engines that had seemed adequate when the aircraft was projected at 50,000 pounds were now struggling to carry 65,000 pounds. Climb performance was poor. Cruise speed was disappointing. Range was insufficient for the transcontinental missions the aircraft was supposed to fly. One by one, the sponsoring airlines delivered their verdict. Pan American and Transcontinental and Western Air had already withdrawn from the program even before the first flight, choosing instead to invest in the Boeing 307 Stratoliner. That aircraft was smaller and less ambitious, but it actually worked. Now, United, American, and Eastern reached the same conclusion. The DC-4 was impressive technology, but it was not suitable for commercial service. The aircraft was too expensive to operate, too complicated to maintain, and too unreliable for scheduled passenger service. Douglas faced an embarrassing and expensive failure. They had invested years of work and approximately $3 million of their own money in an aircraft that no one wanted to buy. The DC-4 prototype sat at the factory like an albatross, a monument to overambition and a drain on company finances. The consortium airlines paid Douglas $91,250 each to settle their commitments, a fraction of the development costs. Douglas executives had to decide what to do with their white elephant. The answer came in two parts. First, Douglas would go back to the drawing board and design a new four-engine airliner based on lessons learned from the DC-4 failure. This new aircraft would be simpler, lighter, and more practical. It would use proven Pratt and Whitney R2000 engines instead of the troublesome Twin Hornets. It would have a conventional single vertical tail, accepting the height penalty in exchange for simpler construction. It would eliminate the complex systems that had caused so many problems. The pressurization system would wait for a later model. The power-boosted controls would be simplified. The aircraft would keep the features that worked like the tricycle landing gear and the basic wing design while discarding everything that had caused trouble. Second, Douglas would try to sell the original prototype to recover at least some of their development costs. Finding a buyer for a rejected airliner would not be easy. Anyone with the technical sophistication to use such an aircraft would surely know about its problems, but the alternative was scrapping the prototype and writing off the entire investment. Douglas began quietly shopping the DC-4 to anyone who might be interested. That bear appeared in late 1939 from an unexpected direction. Representatives from Japan's Mitsui Trading Company approached Douglas with a proposal. They wanted to purchase the DC-4 prototype for use by Japan Airlines, which was known in Japanese as Nippon Koku. The airline was expanding rapidly as Japan's empire grew, and they needed modern aircraft to serve routes across Asia and the Pacific. The DC-4, despite its problems in American service, represented technology far ahead of anything available in Japan. Japanese aircraft manufacturers had never built anything so large or so sophisticated. Douglas saw an opportunity to cut their losses. The Japanese were offering $950,000, a substantial sum that would offset some of the development costs. The transaction appeared straightforward to Douglas executives. A foreign airline was purchasing an American commercial aircraft for civilian use. There was nothing illegal or even unusual about it. American manufacturers sold aircraft to foreign customers regularly. Export controls on commercial aircraft were minimal. Douglas saw no reason to refuse. What Douglas did not know, what the American government did not know, was that Japan Airlines was not the real beer. The airline was serving as a front for the Imperial Japanese Navy. The Navy had been watching American aviation developments for years, and they were particularly interested in foreign aircraft. Japan's aircraft industry had achieved remarkable success with single-engine fighters like the Zero and twin-engine bombers like the G5N, but they had never attempted a four-engine design. The engineering challenges were simply beyond Japanese experience. A true strategic bomber capable of crossing the Pacific Ocean required four engines. The distances involved were too great for twin-engine aircraft to cover while carrying useful bomb loads. American B-17 bombers had demonstrated what foreign aircraft could accomplish. The Imperial Japanese Navy wanted that capability for themselves. They wanted to be able to strike American bases across the Pacific. They dreamed of bombing Hawaii or even the continental United States. But Japanese engineers did not know how to build such an aircraft. The DC-4 offered a solution that seemed almost too good to be true. Here was the most advanced four-engine aircraft in the world, available for purchase through normal commercial channels. The Americans had rejected it, but that was an American problem. Japanese engineers believed they could improve on the design with Japanese engines and Japanese modifications. They would buy the aircraft, study its construction, learn its secrets, and apply that knowledge to build their own bomber. The Imperial Japanese Navy approved the plan and arranged financing through Mitsui Trading Company. Japan Airlines would serve as the public face of the transaction. On September 29, 1939, workers at the Douglas factory in Long Beach, California, disassembled the DC-4 prototype and loaded it onto a freighter bound for Japan. The aircraft was carefully packed in crates with all the care Douglas would show any valuable customer delivery. Along with the physical aircraft, Douglas provided all of the engineering data files that had accumulated during development. Drawings, specifications, test results, performance data, and maintenance manuals. Everything Douglas knew about the DC-4 went into those crates. They even included the wind tunnel model that had been used for 866 tests, the model that showed every modification and refinement made during development. A team of Douglas technicians traveled to Japan to help reassemble the aircraft. They arrived at Haneda Airport near Tokyo in early 1940 and went to work setting up the aircraft for flight. Japanese engineers watched every step with intense interest. They asked questions about assembly procedures, about the purpose of various components, about the design choices Douglas had made. The Americans thought they were providing normal customer support. They had no idea they were teaching potential enemies how to build strategic bombers. When the reassembly was complete, the DC-4 wore the emerald green and silver livery of Japan Airlines. It was the largest, most advanced aircraft in Japan. Newspaper reporters photographed it. Airline executives posed beside it. The wind tunnel model was painted in matching colors and displayed prominently at Japan Airlines headquarters in Tokyo. The airline announced that their magnificent new aircraft would soon begin service on their most prestigious routes. But the DC-4 never carried a single paying passenger for Japan Airlines. Almost immediately after reassembly was complete, after a few initial test flights to verify the aircraft was functioning properly, it was quietly transferred to the Nakajima Aircraft Company at the Navy's direction. Nakajima had received a contract to develop a long-range heavy bomber designated the Experimental Type 13 attack bomber. The specification called for an aircraft with a minimum range of 3,000 nautical miles, enough to reach targets across the vast Pacific Ocean. The DC-4 would serve as their starting point. The Japanese government needed to explain why Japan Airlines' flagship aircraft had suddenly disappeared from public view. They could not admit that it had been handed over to a military contractor for weapons development, so they fabricated a cover story worthy of a spy novel. In mid-1940, Japanese press outlets reported that the DC-4 had crashed into Tokyo Bay shortly after takeoff from Haneda. The aircraft was lost, the story said, and nothing had been recovered from the water. There would be no further statements. The matter was closed. The story was pure fiction. The DC-4 had not crashed. It was sitting in a hangar at Nakajima's facility, being methodically dismantled by engineers who documented every component. The fake crash accomplished several goals simultaneously. It explained the aircraft's disappearance from public view. It prevented American intelligence from tracking what had happened to the prototype. It provided cover for the Navy's secret bomber program. And it discouraged any awkward questions about why a brand new airliner had vanished so conveniently. At Nakajima, engineers went to work with intense focus. They measured every dimension of the DC-4. They analyzed its structures and systems. They weighed individual components. They traced wiring harnesses and hydraulic lines. They created detailed drawings of parts that Douglas had designed. They photographed everything from multiple angles. The aircraft was essentially reverse-engineered down to its smallest details. What emerged from this study was the Nakajima G5N, which the Navy designated as the experimental Type 13 attack bomber. Nakajima gave the aircraft the name Shinzan, meaning deep mountain in Japanese. The name evoked images of massive strength, imposing presence, and unshakable permanence. The Japanese hoped their new bomber would embody all of those qualities when it flew against American targets. The G5N borrowed heavily from the DC-4. The wing was essentially identical with the same platform, the same structure, and the same engine placement that Douglas engineers had developed. The tricycle landing gear was copied directly, giving the G5N the same ground handling advantages as its American ancestor. The overall size and configuration followed the DC-4 closely. From certain angles, the family resemblance was unmistakable, but the fuselage was completely redesigned for military purposes. Where the DC-4 had a passenger cabin, the G5N had a long ventral bomb bay capable of carrying up to 4,000 kilograms of bombs, roughly 8,800 pounds at maximum load, or to aerial torpedoes for anti-shipping strikes. The bomb bay was designed for flexibility, allowing crews to configure weapons loads based on mission requirements. The nose was reshaped with a glazed compartment for the bombardier, providing visibility for aiming weapons. The cockpit was positioned higher and further back than on the DC-4. Defensive armament bristled from multiple positions. To 20mm Type 99 cannon provided heavy firepower, one in a powered dorsal turret and one in a tail turret. For 7.7mm Type 90 machine guns added lighter defensive capability in the nose, ventral, and waist positions. The distinctive triple tail of the DC-4 was replaced with a twin fin arrangement, which was more conventional and easier to manufacture with Japanese tooling. The fabric-covered control surfaces followed standard Japanese aircraft practice. The aircraft was designed for a crew of 7 to 10 men depending on the mission configuration. For power, Nakajima chose their own NK-7A Mamori engines rather than trying to copy the American Pratt & Whitney design. The Mamori was an ambitious power plant, a 14-cylinder air-cooled radial that the Smithsonian later described as the most powerful 14-cylinder engine ever built. Each memorial was supposed to produce 1870 horsepower, a significant improvement over the 1450 horsepower Pratt & Whitney twin Hornet engines in the original DC-4. The Japanese reasoned that more powerful engines would compensate for the additional weight of military equipment. If American engines had been inadequate for the DC-4's weight, Japanese engines with more power would surely solve the problem. Only about 200 memorial engines were ever manufactured between 1941 and 1944, reflecting the difficulties in producing such an advanced design. The first G5N prototype was completed in early 1941. It was an impressive sight sitting on the ramp at Nakajima's test facility. The aircraft was over 100 feet long with a wingspan of nearly 140 feet. It dwarfed every other aircraft Japan had ever built. Navy officials came to inspect their new bomber with obvious pride. Japan was finally entering the era of 4 in strategic aviation. On April 8, 1941, at 2:35 in the afternoon, the first prototype took off on its maiden flight. Imperial Japanese Navy observers watched anxiously as the massive aircraft climbed away from the airfield. Japan's first four-engine land-based bomber was finally flying. The dream of striking across the Pacific was becoming reality. The test pilot's report shattered that dream. The G5N was heavy, even heavier than expected. The memorial engines were not delivering their promised power. The theoretical 1870 horsepower rarely materialized in practice. The engines ran rough and required constant adjustment. They overheated during sustained climbs. Their reliability was poor, with frequent failures that grounded the aircraft for repairs. The flight controls felt sluggish and unresponsive compared to smaller Japanese aircraft. The G5N did not handle like a fighter or even like the twin-engine Betty bomber. It handled like what it was, an overweight converted airliner straining against the limits of its design. Performance numbers confirmed what the pilots reported. Maximum speed was only 261 miles per hour at optimal altitude, far slower than contemporary American or British heavy bombers. The American B-17 could cruise faster than the G5N's maximum speed. The British Lancaster and Halifax bombers were both faster and could carry heavier bomb loads. The service ceiling was just under 25,000 feet, limiting the aircraft's ability to fly above enemy fighters and anti-aircraft fire. Climb rate was poor, requiring extended time to reach operating altitude, and most critically, range fell short of requirements. The G5N could fly about 2,600 meters, well under the 3,000 nautical mile minimum the Navy had specified. The Navy had asked for a bomber capable of striking targets across the vast Pacific Ocean. What they received was an aircraft that could barely reach the nearest enemy bases and would be vulnerable to interception throughout its mission. The dream of bombing Pearl Harbor or striking the American mainland was clearly impossible with the G5N. The aircraft simply could not fly that far while carrying weapons. Nakajima built additional prototypes, hoping that refinements and adjustments would solve the problems. The second prototype flew. Engineers modified the engine cowlings, adjusted the propeller pitch settings, and tweaked the fuel system. Performance improved slightly but remained far short of requirements. A third prototype incorporated further changes than a fourth. Each aircraft exhibited the same fundamental flaws. The memorial engines continued to cause problems. They overheated during climbs. They vibrated excessively at certain power settings. They failed at inconvenient moments during test flights. Nakajima engineers were forced to detonate the engines to improve reliability. Running the memorial at lower power settings reduced the mechanical stress and decreased failure rates, but it also reduced the already inadequate power output. The performance problems became even worse. The G5N was caught in a vicious circle. The engines could not produce enough power to give adequate performance. Pushing the engines harder caused them to fail. Reducing power to improve reliability made performance even more inadequate. In a desperate attempt to salvage the program, Nakajima built two additional prototypes with different engines. These G5N variants used Mitsubishi Mk4B engines instead of the troublesome Mamori power plants. The CAS was a proven reliable engine that powered the successful G4M Betty bomber and several other Japanese aircraft. It had a solid reputation for dependability accumulated over thousands of operational hours. But the CAS produced only 1,530 horsepower, significantly less than even the derated Mamori. The G5N was already underpowered with engines theoretically capable of 1870 horsepower. With engines producing only 1530 horsepower, performance became truly dismal. The G5N flew even slower than the original variants. It climbed even more poorly. It had even less range. The more reliable engines made the aircraft safe to fly but incapable of performing its mission. By 1942, the verdict was clear to everyone involved in the program. The G5N Shinzan was a failure. No engine swap, no modification, no refinement could overcome its fundamental problems. The aircraft was simply too heavy for any available Japanese engine to propel it adequately. The Navy had spent years and enormous resources developing a bomber that could not bomb. The American aircraft they had purchased, studied, and copied had transferred its flaws along with its technology. The Imperial Japanese Army had briefly expressed interest in the G5N as well. The Army and Navy were bitter rivals who rarely cooperated, but both services recognized the value of a four-engine bomber. The Army proposed two variants of the design, the Ki-68 and the Ki-85, which would use different engines and serve Army requirements. A full-scale mock-up of the Ki-85 was actually constructed in 1942 at considerable expense. But the Army watched the Navy's struggles with the G5N and wisely decided not to repeat their mistakes. Every problem the Navy encountered would apply equally to Army variants. The weight problem was fundamental to the design. No engine change would solve it. The Army canceled its variants in May 1943 without producing a single flying aircraft. The mock-up was scrapped. The resources were redirected to programs with better prospects of success. The Navy canceled the bomber program but refused to waste the aircraft entirely. 4 of the 6 G5N prototypes, 2 of the original G5N variants with memorial engines and both of the re-engineered G5N-S with Cathay power plants were converted into long-range transports. They were redesignated G5N-L and given the name Shinshinkai, meaning deep mountain modified. The bomb bays were removed or sealed. The offensive armament was deleted. The defensive armament was reduced. The crew was reduced to just 6 men. The aircraft were assigned to the 1021st Kokutai, a naval air transport unit based at Kokutai Air Base. This unit became the sole operator of all 4 surviving Shinshin aircraft. For the rest of the war, the 4 surviving Shinshin transports flew supply missions across the Japanese Empire. They carried cargo and personnel to bases in Hong Kong, Formosa, Tinian, the Philippines, and the Mariana Islands. Their long range, inherited from the DC-4E's transcontinental design, made them valuable for reaching distant garrisons that could not be supplied by smaller aircraft. They hauled spare parts, medical supplies, and military equipment to isolated outposts. The mighty bomber that was supposed to strike terror into American hearts spent the war as a cargo plane. The aircraft that cost $950,000 and years of development effort became a glorified freight hauler. American intelligence eventually detected the G5N's existence through aerial reconnaissance. Photographs taken from high altitude showed the large four-engine aircraft at Japanese airfields. Intelligence analysts at the Allied Technical Air Intelligence Unit in Australia studied the images carefully and identified the type as a heavy bomber. Following the naming convention developed by Captain Frank M. Coy Jr. in mid-1942, they assigned the aircraft the Allied codename Liz. Under this system, Japanese bombers and transports received women's names while fighters received men's names. The irony was that the Allies assigned this codename expecting the G5N to be a dangerous strategic bomber, unaware that Japan had already given up on that mission years earlier. American commanders prepared contingency plans for the possibility that Japan would use the Liz as a strategic bomber against Allied positions in the Pacific. That attack never came. The Americans did not realize that Japan had already abandoned the G5N as a combat aircraft years earlier. The threat they prepared for was hollow. The intimidating four-engine bombers they photographed were actually just transport planes making cargo runs. The Allied intelligence assessment was not wrong, only incomplete. The Liz was indeed designed as a bomber. It was simply too flawed to serve in that role. Carl Cover, the test pilot who had flown the DC-4E on its maiden flight and taken Orville Wright for a ride over Dayton, did not live to see the end of the war. When America entered the conflict after Pearl Harbor, Cover returned to military service at the request of General Henry Arnold, the commander of Army Air Forces. Cover was promoted to colonel and assigned to oversee B-29 Superfortress production at Bell Aircraft's factory in Georgia. He brought the same meticulous professionalism to wartime manufacturing that he had demonstrated throughout his test flying career. His contributions to aviation were remarkable. He had piloted the first flights of the DC-1, DC-2, DC-3, DC-3, and DC-5, essentially flying the birth of modern commercial aviation with his own hands. On November 27, 1944, Carl Cover died at age 51 in a plane crash during a snowstorm near Dayton, Ohio. He did not live to see victory over Japan Day or to learn what had become of the DC-3 he had tested. A street at Long Beach Airport was later named Cover Street in his honor, a modest memorial to a man who had contributed enormously to aviation history. Lawrence Bell, founder of Bell Aircraft, said of Cover that no single individual in the aircraft industry had contributed more to commercial and military aviation. None of the 6 G5N aircraft survived the war. The 4 transport conversions flew until they were destroyed, worn out, or scrapped. Japanese records from the final chaotic months of the war are incomplete, and the exact fate of each aircraft is unknown. Some may have been destroyed by American air attacks on Japanese airfields. Others may have been cannibalized. For spare parts, as the Japanese industrial base collapsed under Allied bombing by the time Allied forces occupied Japan, no complete G5N remained. The aircraft survives only in photographs, technical drawings, and the memories of those who built and flew it. The Douglas DC-3 prototype was stripped bare by Nakajima's engineers and reduced to components. Whatever remained after they extracted all useful information was likely scrapped for materials as Japan's wartime shortages became desperate. The wind tunnel model that had been painted in Japan Airlines colors and displayed as part of the deception may have survived the war, but its current location is unknown. It may sit forgotten in a Japanese museum storeroom, or it may have been destroyed during the firebombing campaigns that devastated Japanese cities in 1945. The full story of the DC-3 and the G5N did not emerge until after Japan's surrender in August 1945. Allied investigators examining Japanese aviation programs discovered documents describing the Shinchan program and its origins. They learned about the purchase of the DC-3, the fake crash cover story, the reverse engineering effort at Nakajima, and the disappointing results of flight testing. The elaborate deception that had hidden the program from American intelligence before the war was finally revealed. The irony of the situation was profound and instructive. The United States had rejected the DC-4 because it was too complex and expensive for civilian use. Japan had purchased it, hoping to turn American technology against America. Instead, the Japanese inherited all of the DC-4's problems and added new ones of their own. The same fundamental flaws that made the DC-4 a commercial failure made the G5N a military disaster. Douglas understood the DC-4's flaws because they had lived through the painful development process. They knew which design decisions had caused problems and why those decisions had been made. They knew what alternatives had been considered and rejected. They had institutional memory accumulated over decades of aircraft development. When they designed the successor aircraft, they could avoid the mistakes they had made before. They could keep what worked and discard what did not. Nakajima had none of this context. They could see what Douglas had built, but they could not see the reasoning behind it. They did not know which features had been chosen reluctantly as compromises. They did not understand which systems had caused endless headaches during development. They could not identify which specifications had proven impossible to meet. They could only see the final product, not the painful process of trial and error that had created it. This knowledge gap proved fatal to the G5N program. When the memorial engines failed to perform as expected, Nakajima lacked the experience to diagnose and fix the problems quickly. Japanese engine development had not yet reached the level of American or British engineering. When the aircraft proved overweight, Nakajima did not understand the cascade of decisions that had led to those weights. When performance fell short of specifications, they could not identify which compromises to make because they did not understand the original design intent well enough to modify it intelligently. Meanwhile, Douglas applied the hard lessons of the DC for failure to create something better. The redesigned DC-4 that emerged in 1942 was essentially a new aircraft that kept only the name and the basic concept of a four-engine transport with tricycle landing gear. It was simpler, lighter, and much more practical. It used proven Pratt & Whitney R2000 engines. It had a conventional single vertical tail that simplified construction. It eliminated the complex systems that had caused so many problems. The U.S. military designated this new aircraft the C-54 Sky and ordered in enormous quantities. Over 1,200 aircraft were built during the war, making it one of the most produced four-engine aircraft of the conflict. They became the backbone of American military air transport, flying cargo and passengers across the Atlantic and Pacific Oceans. President Franklin Roosevelt used a specially modified C-54, nicknamed the Sacred Cow, as his personal transport. After the war, they supported the Berlin airlift, delivering supplies to the blockaded city in one of the greatest humanitarian operations in history. Many were converted to civilian use and served airlines around the world for decades. The design that failed as the DC-4E succeeded brilliantly in its revised and simplified form. The lesson of the DC-4E and the G5N Shinzan applies far beyond aviation history. Technology cannot be stolen complete. The physical artifact is only part of what makes technology work. The knowledge behind it, the hard-won experience that created it, the institutional wisdom that guides its use. These intangible factors cannot be put in a crate and shipped across the ocean. Japan spent $950,000 to purchase the DC-4E. They spent years reverse engineering it and developing the G5N. They built 6 prototype aircraft. In the end, they had nothing but for cargo planes and a lesson in the limits of technological imitation. Douglas learned from the DC-4E's failure and created one of the most successful transport aircraft in history. Japan copied the failure and produced an even greater failure. The G5N Shinzan, the Deep Mountain, was supposed to cast a shadow across the Pacific Ocean. It was supposed to give Japan the power to strike at American territory. Instead, it became a footnote, a cautionary tale about the limits of imitation and proof that copying someone else's work is no substitute for understanding your own. If you found this story compelling, please take a moment to like this video. It helps us share more forgotten stories from the Second World War. Subscribe to stay connected with these untold histories. Each one matters. Each one deserves to be remembered. Leave a comment below telling us where you are watching from. Our community spans from Texas to Tasmania. From veterans to history enthusiasts, you are part of something special here. Thank you for watching and thank you for keeping these stories alive.